Okay, so this is going to be our very crude video to finish off the last of this lecture. So this lecture 30 and 31. So we left off talking about how incest is bad because you can end up having offspring or descendants that have very rare recessive disorders. So let's talk about one very extreme example, which is self-fertilizing, which is basically the most extreme inbreeding you can do by basically doing it with yourself. Okay, so more often seen in plants. So we can look at how self-fertilization affects genotypic frequencies over time. So basically, let's say that we start off with a population with 30% homozygous dominant, 30% homozygous recessive, and 40% heterozygotes in the middle here, right? After one generation, right, you'll notice that, okay, the p-value stays the same, right? So 0.5 to 0.5. Notice the population's changed. The number of heterozygotes went down by a half, right? Got cut in half. And then that 20% that was lost, 10% went to this side, 10% went to this side. So it went from 30 to 40, 30 to 40. Same thing goes to the next generation, right? Again, we lose another half of the heterozygotes, right? 10% was lost. 5% of that went to the homozygous recessive, 5% went to the homozygous dominant, and so on and so forth, all right? So notice that the homozygotes, right, they just continued passing on their offspring, their genes to their offspring because they're homozygous, right? So this 30% of homozygous dominant becomes 30% homozygous dominant, then you add the 10 from the heterozygotes, okay? Heterozygotes, they lose kind of half, you lose half of that frequency by the next generation, and that half gets split up between the homozygous dominant and recessive ones, okay? So that number kind of changes, what you're adding to each side changes as you go down, depending on how big your heterozygote population was to begin with. Okay, so basically each generation, heterozygotes decreased by half, homozygous increased by, well, half of that half, essentially. Okay, one thing important to notice though is that the allele frequency still stays the same, right? 0.5, 0.5, 0.5. So basically non-random mating as far as associated mating, negative associated mating, inbreeding, negative inbreeding, self-fertilizing, all of these things will affect genotypic frequencies, but not allele frequencies. Allele frequencies stay the same. Right? So this is, even though it's not changing allele frequency, it's still not a Hardy-Weinberg. Hardy-Weinberg assumes random mating, and this is not random mating at all. But when you have these kinds of mating, the genotypic frequencies will change, right? So you get fewer heterozygotes in general, but the allele frequencies do not change. So technically, it's not evolution. Evolution is when the gene pool actually changes. So the gene pool is not actually changing; it's still at 50-50 of big A and small a. All right. So population is not at Hardy-Weinberg, but it is it is not showing evolution. Okay, so mechanisms that actually cause evolution, meaning changes in the allele frequency, we'll talk about just a few examples. So the first example being mutations. So mutations are important because they create new alleles. Now mutations are relatively rare, right? You can see that for these different organisms, the rate of mutation for certain genes is generally very, very low, like 1 in 100,000 at the very most, if not 1 in a billion. Okay, but most of these mutations also are just silent or often are deleterious, right? If you randomly change a letter in a gene, it's probably not going to make it better. All right, now silent mutations are ones that don't affect any amino acid at all, in which case they generally just stay at a very low percentage or they're lost due to genetic drift. Whereas bad mutations, deleterious mutations, are lost even faster than that because natural selection is going to act against them. All right, but once in a long while, when one of these mutations actually makes things better, gives an allele that increases fitness, then you would expect natural selection to make it much more common, right? So natural selection is not random; it's picking up the ones that do good and make them way more common. Okay, for example, if a bacteria evolves resistance to a certain antibiotic, and we keep using antibiotics everywhere, then natural selection is going to make that much more common, that allele much more common in the gene pool. All right, so mutations, even though they're rare, they're very essential because natural selection needs variation. If there's no variation in the population, natural selection can't work, right? So mutations are basically the main source of these new alleles, right? Unless you have some other population you can migrate new alleles from. Okay, example 2. So after mutation, let's look at migration, right? So migration can introduce new alleles or just change the allele frequencies in your population of that you're focusing on. Right, so for example, let's say that you're focusing on studying the population of lake trout in a particular lake, and there's 900 in that population. And in that population, you've already found the allele frequency, which is 0.6 for this dominant allele A. But let's say the flood happens and messes up your results essentially because this flood basically floods a neighboring lake and floods over 100 trout from another lake, right? But that lake has a different allele frequency, it's 0.2, okay? So here's a clicker question for you to just basically try at home to learn from. So having introduced these 100 new trout from a different population with a different P, what should your frequency of allele A be now after this migration event? Okay, so here are your possibilities. So you can pause it here, do the math first, give yourself a couple minutes to do it, and then come back afterwards. So pause, 3, 2, 1, assume you're done, and answer is B. Okay, so I'll show you how that we figured that out. So there's a certain formula you can use, but if you just logically work with the numbers, it would work as well. So I'll show you how to use the formula, then I'll show you how the formula just makes sense. It's fairly simple. Okay, so a couple numbers you need. So these are different letters that represent numbers you'll need. So M represents the number of new trout introduced divided by the total trout in the lake after the introduction. So in other words, this is going to give us a proportion of how many trout were introduced relative to the size of the final population after introduction. Okay, so you'll see what the numbers look like in a bit, right? So we introduced 100 trout, right? The total population after the introduction is 1,000, so that means that the trout that were introduced was 0.1 or 10% of the final population. Okay, that's an important number, so you have to find that first. Then you have to organize your two p-values. So the p-value for your kind of original population was 0.6, so we'll use small p for that, which we already have. Then let's use big P to represent the allele frequency for allele A in the introduced trout, which was 0.2. So this is just given to you in the question. Right, so once you've labeled all the letters, you're ready to use the formula, which is this. Okay, so the formula actually is fairly simple. If you take 1 minus m, it gives you 0.9, right? And you times it by 0.6. So this makes sense because you're basically saying that 90% of the population, right, 0.9, has a p-value of 0.6. So you're kind of weighting that 0.6 by 90%. And then 0.1 is m times 0.2, so this is saying that, okay, 10% of the final population has a p-value of 0.2, okay? So you're basically taking the two p-values, 0.6 and 0.2, and saying that, okay, we want 90% of that final average to be based on this, and then 10% of the final average to be based on this, okay? So by just doing the math, you get 0.56, all right? So notice that when you're migrating in some individuals from another population, the impact of it depends on how many you introduce. So the more you introduce relative to the size of the population, right, 10% is quite a lot, right, the more impact it's going to have, more it's going to drag the p-value down, right? Also, how different they are. So the fact this is 0.2, which is really different from 0.6, means that it has a bigger effect on the final population's p-value, okay? Of course, also if they introduce some new allele that's beneficial, that'll have a big impact as well, right? So example 3, so we've done mutation and migration. Now let's look at natural selection a bit. Okay, so natural selection will act to decrease the frequency of bad alleles and increase the frequency of alleles that increase fitness. Okay, so this can be kind of complex though, because you can't just say this allele always increases fitness, right? Because it kind of depends on what the other alleles are that this individual has, what they do, what the environment's like. So it's a pretty complex thing to look at natural selection, but we can focus on some simpler examples just so you get a feel for what it's like. Okay. So Tay-Sachs disease, right, is a recessive lethal allele. So it's not no kind of wishy-washy thing about it. If you have two recessive alleles, you're dead. Okay, so it doesn't matter what other alleles you have. So assuming that a population has a Q of 0.1, so meaning the frequency of this bad recessive allele in the gene pool is 0.1, let's assume that mating is random. So when I say that mating is random, that you can kind of treat the genotypic frequencies you calculate kind of like Hardy-Weinberg. So even though it's not a Hardy-Weinberg equilibrium, as long as mating is random, you can use Q squared to find frequency of homozygous recessive and so forth. Okay, so mating is random with respect to this gene. What is the allele frequency in the next generation of adults? Okay, so what is Q in the next generation? So pause this, try working out this math. It's not an easy question, but again, this is good practice for you for the final to try working out difficult questions to see if you can find your way there. All right, go ahead and do that. So 3, 2, 1, I will continue. So hopefully you found your answer was B, right? In a way, right, sometimes you can just look at a question and logically figure it out. I mean, we won't have multiple choice in the exam, but notice that we started with a Q of 0.1, right? This is frequency of this bad allele. If you assume that during that generation, in the next generation, all the ones that had 2 copies of this allele died, we lost some of those alleles, then you would expect the p-value to go down a bit. So the only one that goes from 0.1 down a little bit to 0.09 is this answer, right? So that's actually the correct answer just without doing calculations, right? So use that kind of strategy for other courses as well. All right, so let's start off with the p-value being 0.9 and q being 0.1, right? Just based off of this q value given in the question here. Then, because there's random mating, when you see the words random mating, that means that you can use your kind of p squared, q squared stuff, okay? So frequency of big A is 0.9 times 0.9, which is 0.81. Your heterozygotes would be 2 times 0.9 times 0.1, which is 0.18. And then your small a would be just q squared, all right? So that kind of predicts the next generation's born offspring anyways, right? But the small a individuals will die before they reach adulthood, and we're looking at the frequency at adulthood of the next generation, right? So basically, you can cross off this 0.01 small a because they didn't make it, okay? So all we're left with is these two groups. But these two groups don't add up to 1 anymore, so those aren't proper frequencies. So we just have to recalculate it to find out what is the final frequency of big A alleles now that these ones are dead. Okay, so the way we do that is pretty simple. We just take the frequency we have now and just divide it by the total that we have now. So having lost these, right, lost 0.01, that means that this total is 0.99, right? So if we just divide those two numbers, we'll get kind of the adjusted frequency of big A after this small a's died. And for the heterozygote, same thing. So take that 0.18 of what was born and just divide it by 0.99 because 0.01 of them, the recessive ones, had died. Okay, so that same thing for the small a now though. Notice that it's 0, right? You can divide it by 0.99 if you like, it's still 0. It's 0 just because there's 0 survival to adulthood, so we can count it as having 0 fitness. All right. So you can find these allele frequencies using the previous shortcuts. Once you figured out these genotypic frequencies, you can then use them to find the allele frequencies just using the calculations you did before. So I'm just going to use the shortcut method I showed you in pink in the earlier slide. So your p-value, if you want to find it, just take the homozygotes that have that allele, so A1, A2, add half of the heterozygotes, and boom, you have your answer. So find out what's going on with the genotypes. Use that to find your genotypes. Use that to find your allele frequency. All right. So review this again later if you need to make sure that makes sense to you. If you're trying to find Q, you can just go 1 minus this, or if you wanted to calculate it the old-fashioned way, you can still use the same formula as well. So add up all of your small a's, which in this case are 0 because they all died. They're not kind of reproducing right now, right? And then you go half of the heterozygotes, and that gives you your Q value as well, right? So, slightly interesting example when it comes to natural selection is the sickle cell allele, which I talked a lot about before, but it's quite relevant here. So, sickle cell allele is recessive, right? Or actually, it's kind of can be codominant or incomplete dominance, but let's just call it small a for now, just to keep things simple. Okay, so let's say the sickle cell allele, the mutant one, is small a. All right, so if you have 2 copies of the mutant allele, then you have sickle cell disease, which is fairly severe, right? So you have a lot of health problems. You have really bad anemia, so you have very low fitness, and it's generally lethal actually before adulthood. If you have 2 good copies, then you have normal blood. But if you're living in somewhere like Africa that has high chance of malaria, you're quite vulnerable to malaria. It will be very deadly to you. Right? So you have decent fitness, not as bad as small a for sure, way better than that. But if you have big A small a, it's called sickle cell trait, right? So notice the difference. Disease means you have 2 copies of the bad allele. Trait means you have 1 bad copy. That basically shows very mild symptoms as far as sickle cell disease is concerned, right? So that's what we kind of think of the normal allele as being dominant, because you look pretty normal when you have big A small a. You have pretty normal healthy life. But the extra benefit you get is that you get high resistance to malaria. Malaria has trouble infecting you or damaging your cells if you have sickled red blood cells. So this actually gives you the highest fitness if you're living in Africa or other places plagued with malaria. All right. So this is an example where the heterozygotes actually do better than either the homozygotes. So that's called the heterozygote advantage. So pretty logical name. So this results in a higher heterozygote frequency than you might expect in Hardy-Weinberg equilibrium. So this, again, not in Hardy-Weinberg equilibrium. you're getting more heterozygotes than expected due to natural selection. Okay, so in Africa, that's what you see. You see a lot more heterozygotes than you would expect. All right. I think. Oh, okay, that's it. So thank you all very much. So remember that you do have lectures on Friday and Monday. Kathleen, who's an amazing teacher and geneticist, will be teaching those lectures for you. And I'll see you at review sessions and at the final. All right. Feel free to email me if you have questions. I'll check email as often as I can. All right. Thanks everybody. Thanks for a great semester. Talk to you later.